Hello, Algebra 1 students. Mr. Ford here with a quick homework tutorial for 521 Part 1. Whoops, I need a highlighter there, man. Yep, pretty quick here. I already had the answers for 544 written down, but I want to walk you through what's going on here. It's an interesting question. Is it find the slope of the line you would get if you graphed each sequence listed below and connected the points? All you have to do here is go, okay, what is the rate of change? I mean, 5 plus 3 is 8, 8 plus 3 is 11, 11 plus 3 is 14, and so on. Down here it's minus 5, minus 5. Over here, plus 6, plus 6, plus 6. So all you're really doing is finding what you're adding every time. Plus 1.5, plus 1.5, and so on. So that would be the slope. If you were to graph these, you would get a straight line, and the slope would be what you're adding every time, the constant rate of change. For question 545, for the line passing through the points of negative 2, 1 and 2, negative 11, we're going to calculate the slope of the line. We haven't done this in some time, but let's not forget what slope actually is. It's the change in y divided by the change in x. So all we need to do here is find the change in y and the change in x. Now, we usually find that by doing subtraction. I'm going to do negative 11 minus 1 on the top. And I'm going to do 2 minus negative 2 on the bottom. Just be careful about the order here. Remember that if you do negative 11 minus 1, you have to do 2 minus negative 2. So this is negative 12 over 4, which is negative 3. That is the slope. And then we have to find the equation of the line. Now we currently know that the equation of the line is going to go y equals negative 3x plus b. We do not know what the y-intercept is yet in this problem. We could find it a number of different ways. Let's go ahead and use our little formula we haven't seen in a long time, where it's y minus m times x. B is equal to, the tricky thing here is that for y, we're going to use negative 3. Sorry, for m, we'll use negative 3. But for x and y, you could use, honestly, any one of the pairs up above. X is the first number and y is the second number. I'm going to use this first pair because it's got smaller numbers. So in my problem, y is 1, m is negative 3, and x is negative 2. Got to be careful with this one. Negative 3 times negative 2 is positive 6. So b is going to be 1 minus 6, which is negative 5. And that's how I know the equation is negative 3x minus 5. So there you go. That's the equation of that line. What you could do now is you could actually plug in negative 2 and plug in positive 2 and confirm that you get 1 and negative 11. You do, I promise. 546, Allie is making 8 dozen chocolate chip muffins for the food fair at school. The recipe she is using makes 3 dozen muffins. The original recipe calls for 16 ounces of chocolate chips. How many ounces of chocolate chips does she need for her new amount? So, this is kind of like a unit rate question. What we want to know, the question is how many ounces of chocolate chips does it take to make 1 dozen muffins? That's kind of the puzzle here. If we can answer this question, we know everything. Now, what we do know is that the original recipe makes 3 dozen muffins and calls for 16 ounces of chocolate chips. So, let's think about this. We need 16 ounces for 3 dozen muffins. Now, if we go onto a calculator and divide 16 divided by 3, we will not get a whole number answer, but we'll get 5.3 repeating. We can at least write that down. That's 5.3 repeating ounces per dozen. And I like that answer quite a bit because all we got to do now is multiply this by 8 because we know it takes 5.3 ounces to make 1 dozen of muffins. We need to make 8 dozen muffins. So all we're going to do here is take this. We're going to do 8 times 5.3 repeating. I'm going to go on my calculator and just type times 8. And I'm going to get 42.6 repeating. And because I can measure them to the nearest ounce as part of this problem, I'm going to round up and say, okay, she needs 43 ounces of chocolate chips to make 8 dozen muffins. Pretty typical problem that you solve when you're doing baking of any sort. 547, the area of a square is 225 square centimeters. Make a diagram and determine the length of each side. So let's just draw a square. This is a geometry problem, my friends. You guys are headed into geometry next year. I know that the area of this square is 225. The other thing we know about squares is that they only have one side length because all four sides need to be the same. So what this means is that s squared equals 225. What we need is the magic number that you multiply by itself to make 225. And that number is the square root of 225. Which is 15, I think, if memory serves. Oops. Square root of 225. It is. It's 15. Hooray! So this is 15. Let's go ahead and write 15s on the side of this thing there. That's fine. Now here's the other tricky part here. Use the Pythagorean theorem to find the length of the square's diagonal. I'm not really sure how fair this question is for you guys in Algebra 1, but I'll show you how to do it anyway. First of all, the diagonal of a shape is when you connect 2 points and make a diagonal line throughout it. That's what the diagonal is. And what you've done here is you've created a little kind of miniature right triangle. And that right triangle has 15 on both of its legs. And we need to figure out the hypotenuse, which we usually call c. The Pythagorean theorem goes a squared plus b squared equals c squared. And in this case, a and b are both 15. And we already know what 15 squared is. It's 225 from up there. So this is 225 plus 225 equals c squared. That's going to be 450 equals c squared. And what we have to do now is take the square root to find out what c is. It's the square root of 450, which will not be a whole number. It's going to be 21.213. And we'll call it right there. I like that answer. Let's move to the next page, 548. Refer to sequences C and I from problem 541. They are a part of this packet in case you don't have them, but I also copied them here for you. How are these two sequences similar? You know what makes them similar is that they don't. Here's what I think the answer to this question is. What I would want you to see is they do not grow by adding. And they also do not grow by multiplying. I think what I want you to see also, a lot of teams figured this out during first hour today, is that you can get, in this sequence, this is plus 1, plus 3, plus 5. And these guys here are consistently going up by 2 each time. Plus 2, like that. That same thing happens over here with this sequence. If you look at the numbers, you're going down by 6, down by 2, up by 2, up by 6, up by 10. And that doesn't look like anything at first, but if you go one more layer down, these are all going up by 4. So there is this kind of like second layer, this second level of growth going on here. You might have something about that. The second level increases constantly. The numbers from sequence E, which I did not copy down here, are called Fibonacci numbers. They are named after the Italian mathematician who discovered the sequence while studying this. This one is different. This sequence goes 1, 1, 2, 3, 5, 8, 13, 24. 24. That's not right. 21, 34. There we go. As far as this, what is different about this sequence than every other three you've discovered is that it doesn't have any consistent growth pattern going on, other than the fact that it grows by adding 2 previous numbers together. Because if you didn't get this during class today, what you notice about the Fibonacci sequence is that 1 plus 1 is 2. And then 1 plus 2 is 3. And then 2 plus 3 is 5. And then 3 plus 5 is 8. And then 5 plus 3 is 18. You get this pattern where you add the 2 numbers together to get the next one. So you add the 2 previous numbers instead of just adding one thing to the next number. And finally, 549, we got a bouncy ball problem. She dropped a bouncy ball off the roof while Neri recorded its rebound height. The table at right shows their data. Notice that the 0 in the bounce column represents the starting height. To what family does this function belong, and explain how you know? Well, we talked about this in class last week. This is the exponential family. And the reason why is because the numbers are decreasing by a constant multiplier. We are multiplying the same thing each time. What that number is, you have to go to a calculator to kind of figure it out. Well, actually, let's actually answer that in part B, because we got to show the data as a sequence. Is it arithmetic, geometric, quadratic, or something else? Let's go ahead and just do the division. 475 divided by 800 is that number. 290 divided by 475 is that number. 175 divided by 290 is that number. And if I average those numbers together, this is a lot of work for doing for a homework problem, but I'm just kind of just doing what we did in class last week. It looks like the rebound ratio is like 0.6 or so. So I'm just kind of making a note here that the rebound ratio appears to be about 0.6 on average. So what's happening here, if I write it out as a sequence, where we have 800, 475, 290, 175, 100, and then 60. What appears to be happening is that what I'm doing to get the next number is about multiplying by 0.6 times 0.6 times 0.6 times 0.6 times 0.6 and times 0.6. So we're multiplying by the same number each time, which is what's causing this exponential relationship to happen. We haven't talked about this term yet in class if you're watching this video right now, but this is a geometric sequence for that reason. Geometric sequences grow by multiplying the same thing each time. And that's what's going on here. Hey, you guys did a great job today in class. I'm going to see you in the next video. You're awesome. Keep it up.